When dealing with a 480 volts delta utility service and a 480/277 volts Y generator, proper grounding and bonding are essential for safety and system performance. The following steps outline the recommended practices. Firstly, for grounding the utility service, establish the system ground at the service entrance panel using an approved grounding method, such as a water line, building steel, or ground rod. Secondly, connect the ground electrode conductor, abbreviated GEC, to the grounding busbar in the service entrance panel. Thirdly, connect the grounding busbar to the equipment grounding conductor, abbreviated EGC, for the phase conductors. Now let's focus on grounding and bonding the generator. You should tie the neutral and ground together at the generator. Connect the neutral terminal of the generator to the grounding terminal using a bonding jumper. This creates a single point ground for the generator system. Run separate neutral and ground conductors to the automatic transfer switch, abbreviated ATS. Extend the neutral and equipment ground conductors from the generator to the ATS separately. Do not tie the neutral and ground together at the ATS. Next, sizing the equipment ground conductor. The equipment ground conductor between the generator and ATS must be sized as the main bonding jumper. This conductor must have sufficient ampacity to carry the maximum fault current available from the generator. Consider the location of the grounded conductor. The neutral conductor must be connected to the grounded busbar in the emergency panel board. The equipment ground conductor should be connected to the grounding busbar in the emergency panel board. Then connect the system ground. The emergency panel board must be connected to the building system ground through the equipment ground conductor. This ensures that the generator system ground is shared with the building system ground, eliminating the generator as a separately derived system. Understanding the fault current path. In the event of a phase to ground fault in the generator system, the fault current will flow through the equipment ground conductor to the grounding electrode at the service entrance panel and back to the generator. The overcurrent device in the generator will trip to clear the fault. To elaborate, grounding at the service entrance involves creating a low impedance path for fault current to return to the source, which is crucial for the operation of overcurrent protection devices like circuit breakers or fuses. The ground electrode conductor connects the grounding electrode system, such as ground rods or metallic water pipes, to the grounding busbar within the service equipment. This grounding electrode system provides a reference point for the electrical system with respect to the earth. The equipment grounding conductor ensures that all metallic enclosures and non-current carrying metal parts of electrical equipment are bonded together and connected to the grounding busbar. This minimizes the potential for voltage differences between these parts, which could pose a shock hazard. When dealing with a generator, it's often treated as a separately derived system if its neutral is not connected to the building's grounding system. However, to avoid this classification and to share the building's grounding system, the neutral and ground are connected together at the generator. This creates a single point where the neutral and ground are bonded, which helps to ensure that the generator's grounding system is properly integrated with the building's grounding system. Running separate neutral and ground conductors from the generator to the ATS ensures that the ground fault current has a dedicated path back to the source, which is the generator. This is important for quickly clearing ground faults and minimizing the risk of electrical shock. The equipment ground conductor must be sized appropriately to handle the maximum fault current that could occur. This size is typically determined based on the size of the generator's overcurrent protection device and the requirements of the National Electrical Code, abbreviated NEC. The neutral conductor is connected to the grounded busbar in the emergency panel board, which is where the generator's power is distributed. The equipment ground conductor is also connected to the grounding busbar in the emergency panel board, ensuring that all metallic parts of the panel board are properly grounded. By connecting the emergency panel board to the building system ground through the equipment ground conductor, the generator's grounding system is effectively tied to the building's grounding system. This eliminates the generator as a separately derived system and ensures that ground faults have a low impedance path back to the source. In the event of a phase to ground fault in the generator system, the fault current flows through the equipment ground conductor back to the generator. This high current flow causes the overcurrent device in the generator to trip, disconnecting the generator from the system and clearing the fault. This process helps to prevent damage to equipment and reduces the risk of electrical shock. The NEC provides specific requirements for grounding and bonding electrical systems to ensure safety and proper operation. These requirements cover various aspects, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the bonding of metallic enclosures. Article 250 of the NEC is dedicated to grounding and bonding. It outlines the general requirements for grounding and bonding electrical systems. Section 250.24 covers the requirements for grounding separately derived systems such as generators and transformers. Section 250.30 provides specific rules for grounding separately derived alternating current systems. Section 250.50 discusses grounding electrode systems, including the types of electrodes that are permitted and how they must be connected. Section 250.102 covers the sizing of grounding electrode conductors. Section 250.122 provides requirements for sizing equipment grounding conductors. Understanding these NEC requirements is essential for ensuring that electrical systems are properly grounded and bonded. In a 480 volts delta system, one of the key considerations is how the system is grounded. A delta system can be ungrounded, corner grounded, or center tap grounded. An ungrounded delta system does not have a direct connection to ground. While this may seem counterintuitive, it can offer some advantages in certain applications. For example, a single ground fault will not cause an overcurrent device to trip, allowing the system to continue operating until the fault can be located and repaired. However, an ungrounded delta system can also be more susceptible to transient overvoltages, which can damage equipment. A corner grounded delta system has one of the phase conductors connected to ground. This provides a direct path for fault current to return to the source, which helps to quickly clear ground faults. However, a corner grounded delta system can also be more susceptible to voltage imbalances and may require special grounding transformers to mitigate these issues. A center tap grounded delta system has a neutral point established by connecting a grounding transformer to the center tap of one of the delta windings. This provides a stable reference point for the system voltage and helps to reduce voltage imbalances. A 480/277 volts Y system, on the other hand, always has a neutral conductor that is connected to ground. This provides a stable reference point for the system voltage and ensures that the voltage to ground on each phase is 277 volts. The neutral conductor is typically grounded at the service entrance and at each separately derived system, such as a generator or transformer. Bonding involves connecting all metallic enclosures and non-current carrying metal parts of electrical equipment together to create a low impedance path for fault current to return to the source. This helps to minimize the potential for voltage differences between these parts, which could pose a shock hazard. Bonding is typically achieved by using bonding jumpers, which are conductors that connect the metallic parts together. Bonding jumpers must be sized appropriately to handle the maximum fault current that could occur. In addition to bonding, equipment grounding conductors are also used to connect metallic enclosures and non-current carrying metal parts to the grounding busbar in the service equipment. This provides a path for fault current to return to the source in the event of a ground fault. Equipment grounding conductors must also be sized appropriately to handle the maximum fault current that could occur. Grounding and bonding are essential for ensuring the safety and proper operation of electrical systems. By following the requirements of the NEC and implementing proper grounding and bonding practices, you can minimize the risk of electrical shock, prevent damage to equipment, and ensure that electrical systems operate reliably. In the context of the provided scenario, where a 480 volts delta utility service is paired with a 480/277 volts wide generator, several specific grounding and bonding considerations come into play. Firstly, the utility service, being a 480 volts delta system, requires careful consideration of the grounding method. As mentioned earlier, delta systems can be ungrounded, corner grounded, or center tap grounded. The choice of grounding method will depend on the specific application and the desired characteristics of the system. If the Delta system is ungrounded, it's crucial to implement surge protection devices to mitigate the risk of transient overvoltages. If the Delta system is corner grounded or center tap grounded, it's essential to ensure that the grounding conductor is properly sized and connected to the grounding electrode system. Secondly, the 480/277 volts wide generator, being a separately derived system, requires its own grounding system. As outlined in the previous steps, the neutral and ground should be connected together at the generator to create a single point ground. This helps to ensure that the generator's grounding system is properly integrated with the building's grounding system. The equipment ground conductor from the generator to the ATS must be sized as the main bonding jumper. This conductor must have sufficient ampacity to carry the maximum fault current available from the generator. The emergency panel board, which is fed by the generator, must be connected to the building system ground through the equipment ground conductor. This ensures that the generator system ground is shared with the building system ground, eliminating the generator as a separately derived system. Thirdly, the ATS plays a critical role in the grounding and bonding of the system. The ATS is responsible for switching between the utility service and the generator. When the utility service is the source of power, the grounding system should be based on the utility service's grounding method. When the generator is the source of power, the grounding system should be based on the generator's grounding system. The ATS should be designed to ensure that the grounding system is properly switched between the two sources of power. Fourthly, the overcurrent protection devices in the system must be coordinated to ensure that ground faults are quickly cleared. The overcurrent devices should be sized and selected to provide adequate protection for the conductors and equipment in the system. The overcurrent devices should also be coordinated to ensure that the device closest to the fault will trip first, minimizing the impact of the fault. The NEC provides specific requirements for overcurrent protection, which should be followed to ensure that the system is properly protected. By carefully considering these specific grounding and bonding considerations, you can ensure that the 480 volts Delta utility service and 480/277 volts Y generator system is safe, reliable, and compliant with the NEC. Remember that grounding and bonding are not one-size-fits-all solutions. The specific requirements will vary depending on the application and the characteristics of the system. Therefore, it's essential to consult with a qualified electrical engineer or electrician to ensure that the grounding and bonding system is properly designed and installed. Additionally, it is always a good practice to periodically inspect and test the grounding and bonding system to ensure that it is functioning properly. This can help to identify and correct any potential problems before they lead to safety hazards or equipment damage. Grounding and bonding are critical aspects of electrical safety. By understanding the principles of grounding and bonding and following the requirements of the NEC, you can help to ensure that electrical systems are safe and reliable.